Chapter 8 is the last chapter we're covering, matrices and determinants. Now this chapter we're going to be able to get through pretty easily. It's not bad. We've covered matrices before. Matrices systems. A matrice, if n and m are positive integers, then m by n is the matrix. It's a rectangular arrangement of numbers. And any entry we call in the matrix an element. First number next to it is the column. Second number, or first number is the row, second number is the column. So second row, third column is A23. We've kind of done this before. The entries in the ith row and jth column are denoted by subscript A, subscript ij. For instance, A23 refers to the second row, third column. A matrix that has only one row is called a row matrix. A matrix that has only one column is a column matrix. And if it has the same number of rows and columns, it is square. And when it talks about order, we're just talking about the dimensions. M and n are equal, it is square. So if we wanted to look at the order of these matrices, well, this first one has one row and one column, so its order is a 1 by 1. That's it. What would B be? What would its order be? 1 by 4, one row, 4 columns. That's it. C, 2 by 2. D, almost 3 by 2. Yep, 3 by 2. Augmented matrix is when we take a system of equation and rewrite it as a matrix, taking the coefficients for each of our terms. So if we looked at this here, so an augmented matrix would be this here, where we have our variables x, y, z, and it equals the number of their solution. A coefficient matrix is just looking at the x, y, z, the numbers in front of each variable. It's not looking at what it's equal to. So a coefficient matrix is the numbers in front of the variables. They're the coefficients. Augmented matrix is what we're usually used to. Note the use of 0 for the coefficients of the missing y variable in the third equation, and also note the fourth column consists of terms in the augmented matrix. When writing the coefficients matrix of the augmented matrix of a system, you should begin vertically aligning the variables. Again, the variables have to match up. If we go x, y, z, the numbers in each of the columns should be the x, the y, and then the z. They have to line up. Otherwise, it's going to mess everything up. Now, elementary row operations, we're not going to get too much into this because this is doing some of the stuff the calculator does by hand. 3 main things we can do. One is we can interchange rows. So rows of matrices we can flip, we can change them. We can multiply a row by a non-zero constant term, we can scale it, and we can add a multiple of rows together. We can add rows to each other. So if we wanted to, we could flip the first and second row. There's nothing that says we can't. We can also take the original matrix and take this first row and multiply everything by 1/2 to simplify it down. And we can do that multiplication and addition at the same time. So these are different operations that we can do, and the whole goal is to get to this reduced row epsilon form, or row epsilon form, to where this here is that 1, 0, 0, 0, 1, 0, 0, 0, 1. So doing these operations to get there. And that's actually how the calculator does, or in essence, it's doing these kind of operations if we were not using the calculator. Sentences. And again, a lot of this if we had more time than what we do, we would go through and do these by hand. But when we solve these systems, what we're doing is first, we can rewrite it as an augmented matrix. Now the first one, we have 0 for x, 1 for y, 1 for z, -2 for w, and then -3. The second one, we'd have 1, 2, -1, 0, 2. And then 2, 4, 1, -3, -2, 1, -4, -7, -1, -19. And we would want to get this into either our row epsilon form, or better yet, our reduced row epsilon form. Because that would tell us that whatever is here, the numbers in those 4 spots there, would be the solution. And it'd be go about figuring out ways to get it there. And be that adding, subtracting, multiplying, dividing these rows together. Because this here is what we call row epsilon form, REF. Because reduced row epsilon form would get us all the way to the final answer. Because if we get to this reduced epsilon form, the values of x in these other 3 equations are 0. The value of y in these 2 are 0. And the value of z in this last one is 0. And the reason we get there is, well, it tells us here that w is 3. And that's helpful because the equation above tells me that z minus w is -2. Well, I know w is 3. Okay. We can solve for z, telling us z is 1. The equation above it, y plus z minus 2w. Now we don't know what y is, but I know that z is 1, so y plus 1 minus 2 times 3 is equal to -2, because we plugged in our 2 values. -2 times 3 is -6. 1 plus -6 is -5. Add 5, telling us y is, should be, make sure. I did that right. Y plus z. Z is 1 minus 2w. 2 times 3. I went down 1. 3, telling us y is 2. Then we can do the exact same thing with the top row, x plus 2y minus z. X plus 2 times y, 2 times 2, minus z equals 2. 2 times 2 is 4. 4 minus 1 is 3. We can substitute back in to determine that value. The other way we could have done it is typed this whole thing in and got it in reduced row epsilon form, which would have got us those diagonals to 0. And that's it. Gaussian elimination essentially is the same thing, but it's getting to that reduced row epsilon form where we can take that last row of 3 numbers, and that's our solution, which we've done. We've done this already. Yeah. That's it. That's really it. It's pretty much everything we've done so far, especially in the calculator. That's why I said we're doing 2 of them. Operations of matrices, equalities of matrices. There's a rich mathematical history with application of matrices. A matrix can be denoted and is denoted by uppercase letters, and its elements, the numbers inside, are lowercase. Two matrices, A and B, are equal when they have the same order, same dimensions, and their corresponding elements are equal. In other words, two matrices are equal when their corresponding entries are equal as well. So, if the corresponding entries are equal, so if these are going to be the same here, so what should the value of A11 be? What is it? Okay, yes. A12. A21. Yes, and yeah. Because if they're equal, their corresponding elements have to be equal. That's it. Even if we had numbers in front of it, 2 times A21, well, that means 2 times whatever this is should be this value. Just filling them in, setting them up, because 2 times A11 should be 2. And for this here, A11 would be 1. But that's really it. Set them equal and solve it. Matrix addition. We can add two matrices together if and only if they are the same dimensions. So if we look at A, this first one, well, the first matrix is A2 by 2, and it's getting added to a 2 by 2. So since the dimensions are the exact same, we add the corresponding elements. So our -1 is being added to 1. Our 2 is being added to our 3. Our 0 is being added to our -1. And lastly, our 1 is being added to our 2. Well, -1 plus 1 is 0. 2 plus 3 is 5. 0 plus -1 is -1, and 2 plus 1 is 3. Questions on A? Because as long as the dimensions are the same, we can add the corresponding elements. B. The first one is A2 by 3. Second one is a 2 by 3. So that means we can add the corresponding elements in the first one to the corresponding elements in the second. So our first one would be 0 plus 0. First row, second column would be 1 plus 0. First row, third column would be -2 plus 0. Second row, first column would be 1 plus 0. And then we'd have 2 plus 0, and lastly, 3 plus 0. Also, the second matrix here that is consisting of all zeros is actually called a zero matrix, because all the numbers in that matrix are 0. Let's look at C. We do 1 plus -1, -3 plus 3, -2 plus 2. Funny enough, that would give us 0, 0, 0. It's still a 1 by 3. We can't just rewrite that as 0 because those are not the same matrix. And if we wanted to, we could call this matrix A and matrix B and plug these into the calculator, because the graphing calculator will let us do addition, subtraction with these here. We just got to make sure the matrices are set up right. If they're not, especially if we had, say, 2, -7, 3, plus, let's say 5, 6, 2. This is a 3 by 1 and a 1 by 3. This is not possible because the only way we can add or subtract two matrices together is if the dimensions are the same. Now, interestingly enough, we could actually multiply these, but we cannot add these. Questions on this here? All right. In operations with matrices, numbers are usually referred to as scalars. In this text, scalars will always be real numbers. You can multiply a matrix A by a scalar C by multiplying the entire matrix, each entity, each element in the matrix by that value. That's just what that definition says. So the symbol negative A represents a negative times A, which is a scalar product, -1 times A. Essentially another way to say, instead of subtracting, we can add by distributing that negative through. I think it's a little redundant, a little extra to do that. Might as well just subtract as quickly as we can, adding. For instance, the following example, they decided to factor 1/2 out. We can multiply 1/2 through. Because if we multiplied 1/2 through, exactly what we can do. We can also factor it out. I don't know why, but I think it's a little redundant. Note the associative property works. Most properties work with us here. Yep. Now we can solve these with real numbers. X plus A equals B. X plus A plus negative A equals B minus A. Essentially, we can move stuff over. Same thing's true with matrices. We can add and subtract to solve. Now, the reason we have that is, well, we're going to look at this here. We're going to solve for X, matrix X. We want to find out what it is. Now, for us to be able to add or subtract, the matrices have to be the same. So here, we're saying 3 times X, we'll leave it as X, minus 4 times A. Now, our matrix A was given to us as -2, 1, 3, -1, 0, 4. And we're saying this is equal to 2 times our matrix B. And we want to be able to solve this for X. We want to find out what matrix X is. Now, for this to work, matrix X is also going to have to be a 2 by 3. Only way this works. But the first thing that we're going to have to do is try to get X by itself. But what we can do is add 4 times this matrix to the left-hand side, because here we have -4 of them. And if we add 4 of them to it, those are going to cancel out, telling us that we have 3x. But if we do it to one side, we're going to have to do it to the other. -2, 1, 3, -1, 0, 4. Questions on this so far? Now we're going to have to add these together and simplify. So in the first matrix, we're going to have to distribute the 2. We're going to multiply each of these terms by 2. Well, 0 times 2 is 0. 2 times 2 is 4. 2 times -4 is -8. 2 times our 3 is 6. 2 times 0 is 0. 2 times 1 is 2. Plus, here we're going to distribute the 4, do the exact same thing. 4 times our -2 is -8. 4 times our 1 is 4. 4 times 3 is 12. Distribute through the bottom. 4 times -1 is -4. 4 times 0 is 0. 4 times 4 is 16. Next, we're going to add these two together. So we, again, add corresponding elements. 0 plus -8 is going to be -8. 4 plus 4 is 8. -8 plus 12 is going to give us 4. Our 6 plus -4 is going to be 2. 0 plus 0 is going to be 0. And lastly, 2 plus 16 is 18. Questions on how we got to the fact that 3x is equal to this matrix here? Okay. Now, dividing a matrix is not possible. We can't just divide both sides by 3 because we don't have division with matrix operations. So instead of dividing, what we have to do is multiply by a scalar that would reduce the 3 to 1. Because 3 times 1/3 is going to reduce it to 1. So we have to multiply both sides by the reciprocal of the number in front of our x term. Now we can do that through this matrix here. So we can do 1/3 times -8, which is going to be -8/3. 1/3 times 8 is just going to be +8/3. 1/3 times 4 is going to be 4/3. 1/3 times 2 is going to be 2/3. And nicely enough, 1/3 times 0 is just 0. And 1/3 times 18 is 6. And that's it. Then we get our answer. Questions on this here? Now, that is a lot of steps, because we can look back at it in this here, 3x, take 3x minus 4a equals 2b. Well, what we did, if we left it in this terms, is we added 4a to both sides, telling us 3x is equal to 2b plus 4a. Then we multiplied both sides by 1/3, telling us x is equal to 1/3 times 2b plus 4a, and that got us our matrix that we're solving for. Now, if I wanted to, I could grab the calculator and go second matrix over to edit. Matrix A is a 2 by 3. -2, 1, 3. -1, 0, 4. I can quit second matrix over to B, which is also a 2 by 3. 0, 2, -4, 3, 0, 1. Now, what we said that we had at the end, when we didn't type the matrix E in, was we had 1/3 of 2 matrix B plus 4 of matrix A. We added those together and multiplied it by 1/3, which is the exact same thing there, yes? So there are ways that the calculator will do this and get this done for us. The only thing we have to do is get it set up in this here. So that means for this here, the second one, 5a equals 6b minus 3x. Well, if we use it in these generic terms, we need to get this x by itself. So we could subtract 6b from both sides. So like I said, we have 5 times the matrix A minus 6 times matrix B is equal to negative 3x. Now again, we can't divide with matrices, so we'll use reciprocal multiplication. We're going to flip the number in front of x. So again, it's 1. So instead of dividing by 3, we're going to multiply by 1/3. And since it is negative, we would multiply by negative 1/3, telling us x is equal to negative 1/3 times 5a minus 6b. Now, luckily for us, we already have it typed in. So we can say negative 1/3 times 5a minus 6b. 5a minus 6b, yep. Which tells us that it's 10/3, 7/3, negative 13, 23/3, and negative 14/3. 10/3, 7/3, 13. Oh, I just kept 2 of them. 7/3, 0, 23/3. 0. One more time. Negative 14/3. Ah, thank you. Yeah, negative 13. Hard to translate those two. But questions on this here. Not as bad as it's not as bad as it seems. It's more about just getting that variable by itself, and then the calculator will do most of the heavy lifting for us. Because even with addition multiplication, it'll do it for us. Matrix multiplication, we can multiply 2 matrices if the columns of the, number of columns in the first matches the rows of the second, are over and down. Diagonal, we multiply, we get this here. For example, the product of A times B. If we did this by hand, negative 1, 3, 4, negative 2, 5, 0. And we multiplied it by negative 3, 2, negative 4, 1. The way we multiply these two matrices is over and down. We're going to go over and down. So we'd have negative 1 times negative 3. And add to it 3 times negative 4. And if there was another number after another column, another row, we would keep going in that fashion. But since there's not, we move on to the next one, over or down. So we say negative 1 times 2 plus 3 times 1. And since there's no more columns, or sorry, no more rows to multiply through, we're good. And we do it again. We go 4 times negative 3 plus negative 2 times negative 4. And then 4 times 2 plus negative 2 times 1. And we do the last one, 5 times negative 3 plus 0 times 4, negative 4. And lastly, 5 times 2 plus 0 times 1. Now we multiply and add. Negative 1 times negative 3 is 3. 3 times negative 4 is negative 12. Negative 1 times 2 is negative 2. 3 times 1 is 3. 4 times negative 3 is negative 12. Negative 2 times negative 4 is 8. 4 times 2 is 8. Negative 2 times 1 is negative 2. 5 times negative 3 is negative 15. 0 times 4 is 0. 5 times 2 is 10. 0 times 1 is 0. And lastly, add 3 plus negative 12 is negative 9. Negative 2 plus 3 is 1. Negative 12 plus 8 is negative 4. 8 plus negative 2 is 6. Negative 15 plus 0 is negative 15. 10 plus 0 is 10. Or we could have done what? Use the graphing calculator, type those in as A and B, and said A times B, or AB. Y'all remember doing these in the calculator? Yeah. That's also part of the reason why I went decently speedy through that, because y'all remember doing this, and for the most part, you're going to do it by calculator than by hand. But that's it. That's also part of the reason we did both of these sections in one day.